I'm standing between you and lunch, and I respect that, but I think we have a fairly interesting topic here. I'm going to talk about design patterns for scalability and availability, especially in the context of trading systems. But these patterns, design patterns, I guess, are generally usable, but there are some constraints when it comes to trading systems, which makes them applicable, and maybe they are used in more extreme versions in the trading systems than they would be used in other software systems. But you will see some of them in other systems as well. So I'm going to start to give you a very crash course of what kind of system and what we're solving for. So Saxo Bank is a global online investment bank, which is a broker. We have offices in 25 countries. We have clients in 180 countries, trading both over UIs and APIs. We offer access to the global financial markets, so we're essentially connected to broadly each and any exchange, any market you can imagine. We are on the third generation of a technical platform and evolving. It's Microsoft-based, mostly developed in-house, so most of the components and whatnot I will show you on the screen are actually in-house. We're serving tens of thousands of concurrent users, and more than, actually I will get into more of detail on the numbers, but essentially very high transaction peaks, both in terms of online users. And that's also the time where we need to be responding even more timely than when it's silent. So there isn't really a trade-off. So the business model is essentially we're taking liquidity or things from the market, and we're providing that to end client globally. A lot of products, and there is also back office risk management and other stuff. So that's broadly the business model, and then we essentially make money on commissions and other fees related to your trading. So this is just to show you that it's we're covering a very broad range of asset types and instruments. I'm not going to go into detail, but it's global and very wide variety of products. So, and the workflow and service requirements for being able to deliver this globally is obviously based on some fundamentals, King authentications, authorizations, subscriptions, setting profiles and configuration. But then you have the different legs of trading and execution, where you have tradable quotes, request for quotes, DMA, different kinds of way to interact with the markets. You have the order management, where you receive and process orders, you route orders to the market, you might bundle orders and send them in batches, and you get execution specs on orders. Then you have the whole risk management aspect of it, and it's actually more than just when you want to trade, checking that you have money on your account, because your current positions might be in deficit. You actually might hold more positions or more assets than you have money on your account. That's called leverage trading. And the actual value of your portfolio is not just a linear function of you know, the current profit losses on each and every of your assets, but it's a non-linear function. So you essentially need to look to the whole portfolio of the client every time he trades because of currency exposures and whatnot. Then you have pricing and reference. So there's price formation, price distribution, and the reference data around the instrument you have on the platform. And then you have the content, which is chart, news, analysis, and research. I will largely today talk mostly about the trading and execution and the pricing side, because that's where those more extreme requirements emerge. and to maybe to some extent risk. That's where the extreme requirements for throughput and latency occurs that have given rise to some of these maybe non-traditional patterns. So we are seeing in excess of 20,000 concurrent online users. We are operational and open 5.5 days, 25 hours a day, which means there is no downtime, there is no time to, apart from the weekend, to upgrade the system. We process in excess of 500,000 price updates per second. That's essentially a price coming in, and we might need to react to that price in a very short amount of time, route an order, do something on behalf of a client, and so forth, reevaluate the client's holdings based on the price fluctuation. We are doing intraday execution of 2,000 trades per second, and 2,000 trades per second, and that's business trades, but each and every trade is also at least, coming with an order request and some state changes on the actual order that trade generated. So this is actually real trades, but a trade generates a lot more messages in the system, actually, say, roughly maybe 3 to 5 messages per trade, just for that trade to come into life, so to say. We book over 1 million trades per day, 160 unique users, and we're trying to maintain latencies in the single-digit millisecond range throughout, from we receive something until we react to it, essentially. So that was just to give you a small crash course in the kind of technical challenges we have. So here you can see one of our clients sitting in the platform and this is obviously an end user sitting on a tablet, but there might be an API, which in turn has a lot of other users, or he might sit on a web or a desktop application. So the business challenges also is to provide a unified and compelling client experience across devices, platforms, and across the world. Do that in a cost-efficient way by using as much technology sharing as possible, reuse, trying to avoid duplication and proliferation of technologies. So essentially, we serve all our system from a single system, so we don't have multiple systems across geographic locations, but it's a single instance systems where we host all the tenants in the same infrastructure. Faster time to market and flexibility, adding new products, features, and sophisticating of existing products, and entering new geographies is typically also what comes up. Compliance and regulation. Financial services is a heavily regulated market, and we also face the challenges of multiple regulators as we operate in 25 countries, and we will white label this platform for other financial services providers to use it, which means we're indirectly regulated in even more markets. And that is a challenge when it comes to having auditability and traceability and your processes in order and stuff like that. So what are the critical business flows where milliseconds matter? It doesn't really, if it's creating a client, it's okay if it takes more. That can take some longer time. But essentially you have the markets here, we have the liquidity, and there are two flows. We get some price in from the market, and we need to get that out to the client in either a clean form or in some kind of manipulated form. And then the client makes an order and wants a trade, and we might or might not want to go out in the market here and get that back to the end client if he's sitting on a UI. But these are essentially the flows we're optimizing for. So a price comes in through some feed handler where you normalize it. It might be different protocols. It goes to some level of aggregation. Then we do some calculation and then send a price out to the client. So there are multiple steps here. And yes, we get 500,000 in here. This price might also hit downstream services for them to react to. So it's not just going out to the end client here, but we have internal services that need to react to the price, route an order, or do whatever. And then you have the actual client. He wants to trade. He sends an order. We do some calculation. You do some handling. You decide if you want to go out in the market. You get the order back. You get the trade back, and you need to get it back to the client. So these, and before we accept your order, we do a margin or a risk check, essentially, saying if you're allowed to take this position or not. So, crash course in or in trading, and you can see there is also a challenge here of exponential business growth. This is a generic measure of number of business events per day over a period of time. So the system needs to scale, it needs to be resilient, and so forth. So trading systems, I don't know if you have read about the Reactive manifesto, but trading systems are actually, I would say, the definition of a reactive system. So if you look at the core design principle mapped to the tenets of reactive, you would see reactive systems should be responsive, i.e. they should respond to the user in any condition. So we use casual and eventual consistency to allow to be responsive. We use horizontal scaling massively, or partitioning, sharding, segmenting of workloads, work sets to be able to scale and be responsive. Asynchronous kind of fire forget action where it can be supported. And we have very high throughput and tight latency requirements. Elastic, we strive to be able to scale out on commodity hardware using horizontal scaling of work set. And be able to grow capacity swiftly by horizontal scaling. Resilient, redundant, no single points of failure, running fully active. So there is no passive service. It's actually active and maintaining the state that the active one has, with automated seamless failover. In some instances, when we do risk checks, for example, we actually send the risk checks to two servers, and we take the one that responds first back because we know they're eventually and casually consistent, and we're good enough with one of them responding because the other one might be garbage collecting, for example, or whatever at that point in time. It's very unlikely that the two of them do the same time. We need to be able to survive with a reduced service if we have a massive breakout of a full data center or a communication line or whatever. Message-driven, it's event-driven and message-driven at heart. Loosely coupled systems using topic-based publish-subscribe messaging, essentially. So a little bit about our technical environment. I'm not going to go into deep. We're running purely on Microsoft. It's .NET, C#, Visual Studio, TFS. So for most of the applications you see in here are actually Windows services or IIS-hosted apps. We have a lot of shared components for business logic and caching that's used throughout the system. We use Elasticsearch Kibana for feature tracking and some monitoring, SCOM, and so forth. We are running large parts of the critical infrastructure on bare metal because we cannot get the performance when processing 500,000 price updates per second on a virtualized environment, let alone in the cloud. It starts breaking down. And even doing multicast is a challenge in those environments, actually. So the architecture, very high level. We have the end clients here. We have an open API. We have another API. We have some shared components. We have a message bus, high performance. There's some infrastructure services. I will go into some of those. There are some core services around order management and risk management. There is some connectivity to the market. And then in the end, there is some databases here as well. And as I said, we're going to focus on core and trading and execution. There is also a back office system and money going in and out of the bank as well. I won't cover that in this talk. So essentially, the front ends are HTML5, very rich single-page applications. And they're hosted in native shells, so we can distribute them in the app stores, but essentially it's the same code base running whether you log in on Android or on iOS or on your tablet. It's just essentially different layouts, and we are developing this HTML5 to be in the desktop application as well. Essentially the same components will be repackaged in an Electron shell in that instance. And all those applications are served by a open REST-based API. And here you also use sticky sessions because there is a lot of session state you need to maintain, which instruments are the client watching and so forth. A lot of business logic is actually front-loaded and executed already in this layer, in this process. And the API is REST-based with streaming over WebSockets out to the client. We don't use that internally. Then we use multicast. There is a high-performance messaging middleware with horizontally scalable persistence, so we don't need to write every transaction to the database, but we can essentially just publish it and be rest assured that it soon enough will hit the database or the downstream services interested. There are some back-end infrastructure services. They are horizontally partitioned, fault-tolerant, with fully redundant, running in multiple data centers, and also traditional databases, but running in mirroring high availability mode. Those are single instance, as we do a lot of the scaling actually up in this layer. And I will come back to that because we actually want to avoid the database as much as possible, because that's usually a performance bottleneck in any system when you hit a specific scale. But definitely it adds some complexity, or a lot of complexity. So there is active meshes of segmented, partitioned workload, and these might be partitioned on different axes. So For orders, it might be around the actual instrument. For the risk, it might be an individual client residing in one segment. And then some large grade shared components, they encapsulate some core business logic around trade capture, order capture, and some of them are just essentially caching data in a way that's optimized for the actual use. So it's not generic caching, but actually data read up and kept consistent and structured in a way that's optimized for the specific use, whether it be finding commission rules or deciding where to route an order, which is all semi-static configuration that you can change intraday, but you don't need millisecond. It can take some time before that actually gets through in the system. So what are some of the interesting patterns if you look at all this? Well, we use asynchronous transaction logging, so we actually accept the business transaction, whether being an order, whatnot, before we have written it to a database. We're pretty sure that it will at some point in time hit the database and be secure. It's actually tracked at multiple levels, and there is a replay, restore mechanism on this message bus as well. We use publish subscribe messaging heavily, using multicast over using a optimized binary protocol, so there will be no angle brackets, there will be no JSON, there will be no it's bytes paired down to the metal. So we take everything coming in, normalize it, and in an optimized manner for this use case, and that goes for both of those flows we saw on the screen, both getting prices in and handling transactions. We use meshes of partition service. They execute real-time automated business processes in action. That might be routing an order to the market or sending in a push notification to a client that you're a little bit too close to being stopped out now, or even in the end actually protecting the end customer and closing his position if it goes that far. And that needs to be fairly quickly done, so we cut the losses for and protect the client and ourselves from any losses. We use a witness server to achieve the seamless failover here between two essentially active instances of a component. They are essentially receiving the same stream of information. They maintain the same state, and one of them is deemed active using the witness server, or if they are contact with each other, and it's only the active one. So they go through all the hoops and loops and process everything. They even make the decision, but it's only one of them that then actually executes the decision and sends out, this is the way it's going to be, and that can flip very quickly if one of them goes down, and both of them can actually respond to requests. You can even have more than two actually if you want to scale out. But only one of them will actually generate the business, the automated business transaction based on some input. Also, a lot of monitoring and tracking going on. It becomes crucial when you're all message-based, when things goes fast. So we and that's use both just bespoke logging of data, but also using Logstash and Kibana to do tracking and so forth on the back. The Open API actually also has a scalable in-memory session management, and now it looks like a large monolith, but it's actually divided in relevant microservices or service groups hosting specific functionality, one that can be deployed and independently. One can be order and trade management, one can be portfolio, one can be charts, for example, and there is a range of those, but these all share a common session. So the client logs in once using the single sign-on system, and he can use that token to access any endpoint, and all these sessions also share a common streaming channel. So any of these services can actually, knowing your session ID, can stream a message to you over a single channel, because we don't want the end client here to need to understand the underlying architecture and have like 25 streaming connections for each and every service or endpoint that needs to do streaming. So there is a common framework around that, but then it's fairly compartmentalized. So in the humble beginnings, some of the people in the room here have been with it. Essentially, you write a system fairly traditionally. The client comes in, he makes a request, you register it in a database, you send a message back to the end user, and now we need to get this out to the system, whether it be a risk system or some sort, and then it needs to get out to end users or back office. There might be multiple. So now you have a guy here essentially pulling the database for new things and pushing it out. And this polling obviously introduces a latency and wait time. And then if the more layers you have here, the more polling you have. So here you can say there might be another round of polling, and if you compound that up from the time something is done here until someone can react to it, a system or human, a long time can have passed. And actually the market might have moved against you, or the information is too old. The database here becomes a bottleneck. You can obviously shard a database, that's also complex, but this little spindle here, it's not a spindle anymore, but the disk where you keep the transaction log on will become your scaling point. And this polling, there is only so much you can get that down to, and the more you squeeze it, the less throughput you get in this sense. So you need to give the writers some chance to get in for the readers. So your throughput here and latencies are essentially capped by this lump here in the middle. Yes, I've been through this. So instead, what we do is we use something called as asynchronous transaction registrations, and essentially try to abolish any, say, no I/O, but any database I/O in the transaction path at least, and we try to avoid even network I/O to the extent possible. I mean, that's always a balance. But essentially, in this case, the client makes an order or a trade request, it hits some front-end, Open API or whatever, that generates a new trade message that is essentially a single write on the network in an optimized binary format. Someone is having a birthday. Congratulations, Darren. So it's a single write, a single network write on a socket, and then all downstream services here needing that reads that message and consumes it and does whatever it wants with it. So this is fairly close to what you would say event sourcing or whatever you call it. And they take this message, put it into their internal structure and start reacting to it or process it or do whatever. And in this case, so essentially the transaction is fully verified and accepted very early on here. And essentially when this message goes out, it's a fact. It has happened. Now it's just for the downstream system to consume it. And we have confirmed the client actually. So the transaction message is actually persisted in memory in at least two of three machines, so we can replay and apply some resilience. This is essentially just a transaction log or buffer of whatever has transpired during the last week or so. So any service here can be down and do a replay of what's happened and come up to speed. So this means that these guys that were in the previous pictures, they were kind of 2 layers down with 2 rounds of polling, now essentially get the message immediately and can react to it immediately. And more often than not, this person here actually reacting to it is not a person, but a computer or an algorithm. You could argue that if it was a human, it didn't matter that much. I think humans start seeing delays of maybe 100 to 200 milliseconds if they're consistent. But yes? No, the client sends in a request. The request is processed in the front end and accepted. So you verify basically everything using in-process caches and whatnot. All the state is there to be able to fully, validate and verify the transaction with the only acceptance of the actual pre-trade check, which actually, or the risk check, which is a single round trip that's still there. You could remove that as well, but that is a bit more complex. And then the message is now the transaction has happened, but we try to minimize process jumps, I/O. I mean. That even goes for simple logging, actually, which is done asynchronously in here as well, to the extent it's done. And then the transaction is picked up, processed, and aggregate is sent out. And then you have the critical piece here of actually getting the transaction to rest. Is essentially you have a set of trade registration services which asynchronously writes the transaction to the database. Yes?
I'm curious if when you verify the state, can you because the entire state might not have been committed to the database, where do you check to know the entire state?
The entire state is actually, or the entire state or state change is kept in this message. So this message it's a message. So actually when this message hits the database, it will update multiple tables from, your orders tables to your audit logs to whatever. So That's also key. These messages, they are, you know, real business level events. They carry a fair amount of context and data with them.
What I'm
Yeah.
not really getting is if the message has not yet hit the database, right? And I'm sending another message.
Yeah,
Fail. How do we
the messages here from a single source, they come in order. So if you followed from the beginning, we have sticky sessions, so each request will end up in the same server. So the messages from a single session or single user will actually be processed in order broadly. So then, which means that this guy actually knows that even if this message hasn't hit the database, it knows that I've sent this message and incorporated it in whatever state he has up there. So which means when the next message comes, that is taken into account. And the same goes for these guys down here. They will see the messages from a single session in order. Lo and behold, there are race conditions here. So because that guarantee essentially only holds for a single source. So there are some race conditions you need to solve in this scenario as well, which is usually, if you look at the problem, something you can do because the messages or the entity is usually either partially owned by parts of the system or there is one owner right now of that entity, actually the one that sends out the messages, or you need to serialize some stuff. Good questions, and I like that you speak up because interaction is good. Yes?
When does the actual transaction happen? Like, don't you have to subtract it somewhere?
The actual transaction happens when we have accepted it here. The rest of the system is essentially eventually or casually consistent. I know once I've published this message that it will hit the downstream, it will hit the database, it will hit the margin server, my risk system in the correct order. And these guys, they're essentially just keeping an in-memory state of what's in the database in essence, which means that these guys down here, they have an in-memory state, so they don't go to the database either normally because they essentially, yes, that's why you have this snapshot service here. So they start up, they read a snapshot, and then they join this message bus and say they look at this snapshot and see there's some sequence numbers there, and then they join this message bus and say the snapshot I've gotten has this sequence number. Please replay from that. That gets replayed. You incorporate that into your state. Now you're online, and new messages will come in. And so they don't touch the database either in a running state. They essentially just use the database through the snapshot service to prime their initial state and then get a replay and be online with the current state of the system.
So this is basically an actor model with stateful actors.
Yes, you can. That's a good analogy, actually. Yes.
This message bus actually looks very, very well, but the question is probably scaled up. So, and you keep the state in the message bus. So, how would you make sure that these actual machines are consistent and your status is just consistent across all the machines?
Could you repeat the question?
How would you actually
the state in the message was consistent.
Yeah.
I'm not sure I fully follow. The message bus it's essentially just a transport layer, something built on top of multicast. So
Wouldn't you actually keep the status of your system in that message bus?
not fully, because the message bus essentially is just, you know, transporting bytes. The state is kept. There is a buffer here of the recent state changes. These guys have their state in RAM, and this essentially have the persistent state of the system.
But anyways, in the RAM, actually, you have different machines.
Yes?
And any client can hit any of those.
Yes?
So you might have different status of your system in different machines.
Yes, that's why I say the whole system is built around casual and eventual consistency. But casual and eventual here is sub-millisecond, which means it's very unlikely that you and usually also one guy will hit the same node typically, but one service speaking to this guy will typically hit the same node. So
I have another question.
yeah.
Since the architecture, can be great, everything is low latency. Where do you position the servers so that, because if you have servers in Copenhagen and you talk to
They are positioned. Most of them are actually in Copenhagen. There is also servers in closer proximity to the market in London, for example. So.
but would that not even, does it impact this latency? It's quite
Yeah, the transport latency is obviously something you need to take into account as well when you do all this. But I don't think that's the largest latency. I mean, it's going the last mile out to the end user. If I have a client that is a sheep farmer in New Zealand wanting to hedge for his sheep or whatever, he's far away from a lot of it. But this is mostly also to protect, to also a protection for us not to take too much risk. So we're actually good with measuring the internal latency here. But the client, it's also about the clients, because he might get reactions or he might not get the price he saw on the screen and so forth. So if that last mile also becomes too long, then it's a problem.
I would rather think about algorithmic.
Yeah. In the end, the kind of things we do, this is not high frequency. It's not high frequency algo trading. And we do some algorithmic trading, but I wouldn't label it as, and we let some of our clients do as well, but I wouldn't label it as high frequency. That's why I've consciously here talked about milliseconds and not microseconds or nanoseconds. There are some parts of the systems where we talk microseconds, but that's usually within a box in London somewhere. But that's very small micro workflows in this large scheme of things. So scalable, resilient, we can have very high throughput, low latency, and be purely event-driven using this approach. We have talked about some of the flip sides, like, yes, you have some race conditions you need to handle in some cases. that can be mind-boggling. But that's also inherent in some way with the market. That's like on a micro level. If I order something, from Amazon, I cannot cancel that order because it might actually be on the way to me. I might be able to cancel it if they haven't start sending it to me, and this happens here at the microsecond level. So you have some inherent race conditions just in the business domain, but it's on a different scale than when you order something from Amazon. But there might be a trade actually on the wire to you when you want to cancel a transaction. That will obviously get rejected, that cancel transaction. And we might even say, we have accepted your cancel request, we're forwarding it on, and then someone says, sorry, we couldn't cancel. There is a bit of a final twist here I want to go through with asynchronous transaction registration, and that it's fully active, which means essentially you have 2 failure zones or server rooms or data centers where you have front ends receiving, accepting transactions, sending them out on this message bus, which is spread over both of them. Then you have the transaction logger, which essentially receives the transaction, and one of the guys actually write the transaction to the database in the end. It gets shipped to the mirror database and gets successful, and the other guy essentially, so these messages also here needs to be idempotent, or so writing 2 of them should still leave the database in the same state, which is very easy in this case because you essentially just have a unique ID on each message, and if it's been processed, you say. This means very easily there is no failover, there is no. Everything is running all the time. I can add multiple of these. I can restart these guys without having zero impact, which is a very nice property, because always when you have this failover of any kind, there is always a chance that it might not work when you need it to work. So this is actually exercising the same code path all the time, all the day, every day. Obviously, we're hitting this guy quite a lot, but in the end, we have also said that we're not so dependent on the throughput here that you tend to be. So we are happy to take that hit for the simplicity, so to say.
About this failing, so you have different steps if it is failing because there is.
Yes. I mean, fails here. It's a bold word, but in essence, if this guy has won the race, you essentially get a message back saying message was already there. But if the connectivity to the database is down and none of these guys can get to the database, those kinds of failures, they retry. That's a good point.
What's the rate on the service bus and which actual bus is it?
Right now, we're using, that's a commercial product. There are several products out there. We're using Informatica LBM format 29 West. TIBCO has something, IBM has something. There is also open source one called Aaron right now out there that you can use to get these very high, low latency, predictable latency speeds. And there are also, more zero MQ and other stuff that you can use to implement this pattern, but you might not be able to scale it to distribute 500,000 price updates per second, but that might not be your use case.
Is that your rate?
Yes, that's 500,000 price updates per second. That's what we essentially pump out through the system and react to. And they are essentially multicasted out over on the network. Yes, I think we've gone through this. So here you have the transaction fails gracefully. So there are two levels of failure. One is graceful and one is ungraceful. And on an ungraceful failure, you retry. And then on the database layer, we use traditional mirroring or high availability that's available in a lot of SQL or Oracle or MySQL or in a NoSQL database. There are different ways to achieve this. But the same principles can be applied. So that's why I've also chosen to keep this fairly technology agnostic and free from code, because this is actually generally, it just depends on what are your business requirements. You can design a system like this and get some of the benefits by applying different technologies on the different layers, depending on we might have some very extreme requirements, but there are other use cases where you actually can do similar things and achieve some of the benefits. And you might not be as hardcore with your serialization, deserialization. You might actually also do some more I/O in the path, but in general, it's applicable as a design, high-level design pattern. So it's not all about architecture and technology and people or architecture and technology and patterns and so forth. It's also the people. Try to hire best, cultivate the performance and winning culture, cultivate the engineering mindset. It's very, because yes, we're solving a business problem here, but maybe not in the most straightforward way, because we have some extreme requirements, which means you need to have an engineering culture, not just I'm going to take the shortest path to solve this problem to the business kind of way. So supporting management. There's some process, tight change and release management processes, test and quality processes, automated testing and so forth. And when shit hits production, you need to have a incident management process in place that allows you to respond very quickly when there are issues. And we get worried. You could say, yeah, we're fully resilient and redundant, but if one of the nodes is down, that's still cause for an incident, because we don't want to run with a single point of failure. That goes for any layer in the stack. So it's not just relaxing when we still have a failover. So because when that guy is down, you're essentially running not as you intend to do, with reduced resilience. And that goes all the way through the stack, from network lines to hardware to applications. Monitoring goes without saying, real-time and reactive. Cooperate closely with the business, agile methodology. Hamper complexity. This is complex, but there is still some simplicity in the design, and if you try to stick to some few core principles, then you essentially, yes, it's complex, but you have some very high-level constructs that you apply and reuse to solve some of the challenges you have throughout. So, some learning points. Well, if you are designing an architecture that needs resilience, scalability monitoring, that needs to build in and taken care from the start, because it's fairly complex and it's a huge estate. There is also, I don't know if you have listened to Martin Thompson, but there is, and he speaks about mechanical sympathy. That's really optimization and understanding things, how things hang together from the CPU down when you optimize code. But that also goes on a macro level, so which means you actually need to synchronize things so it's optimal all the way from the way you have your network, firewalls, the way you divide multicast groups down to your application, how your application is structured. And all those strings actually need to tie together, because if you at one layer introduce something that breaks that, everything need go to a single firewall, or you design your topic space in such a way that all messages, even if they are on an application level nicely divided into topics, they will actually hit your CPU on a single core and need to be processed and then discarded. So they go into the machine, they go into your network card, they go up to the operating system, they get delivered to your application, and someone just says, I'm not going to use it. And if you do that, and the logical design might be very beautiful, because I'm just subscribing to updates for Apple here, but in the background you're getting hit by 500,000 messages per second. So it needs to hang together all the way, not just the logical design actually, because this goes down to physical design as well, and so forth. So do gradual rollout, provide rollback and backwards compatibility to decrease operational risk when you do large architectural changes. Comes as a cost, test and verify very thoroughly. And then last but not least, this might happen to you while you're trying to do this, so be careful. I think that's it for me. If you have any further questions, please, yes?
Yeah, I think I've seen a similar presentation by you about 4 years ago.
Yes.
And I'm just thinking now, how old is your architecture now, and how is it holding up? Because
It's holding up. I can tell you. To the two best days we've had from both, I would say, a business perspective and technology perspective, was actually the Trump election and Brexit days, where the system actually hold up very good, both technically and for our clients. And these were record days by all standards. Actually, I think we have seen in terms of number of transactions and throughput, of the top 10 days, 8 of them has been the last years, the last 365 days. And we have maintained response times and up times and kept our availability at a very high level during those. But they're continually We're continually optimizing and redoing things in the small.
But the fundamental architecture is holding up.
The fundamental architecture is holding up, but we continually tweak and optimize and find things, and from a inefficiency standpoint that we need to do. But usually the problems are not macro structural, they are local, more local than when you have another kind of design where some of the problems you face are more very structural on a macro level. I mean, there might be structural issues within a component as well, obviously.
Yeah, we have a question about the releases. So, for example, how often do you release and when do you release? So you said
It's a mix, actually. The most parts of the estate is released weekly on Saturdays, which is very good for being a regulated bank. And we do a lot of releases and a lot of changes. Some of the components you see there can actually be released where we have the best, resiliency and so forth. They can be released intraday as well. We typically don't do it unless we don't really have to. But if we have to, we do that, and we can do rolling upgrades without significantly interrupting the business on most of the layers.
But as I understand, your system has so much services and so much parts, and if you want to introduce some feature, it may affect some of the parts.
Yes.
It's quite hard to schedule this release.
Yeah, but that's why I say feature flags, continuous delivery, be backwards compatible, handle missing fields gracefully. All that needs to be in place if you're going to run those amount of components on that scale. So you can roll back, roll forward with some certainty. So it's not, we very seldom do big bang forcing changes where we need to, push something out in the weekend over everything. That's just not, or it's feasible, but it's not, it's too risky. And also rolling it back is very risky. So that's more done on a component service level.
I would like to ask about testing strategy, because testing one module is fairly easy, but how would you test the whole system?
That's in this weekly release cycle thing. There is actually a release test environment where we do both automated and semi-automated and manual tests on what is going to be deployed in the weekend. So a lot of the testing is done, both using unit testing and some integration testing in your continuous deployment pipeline, but that's obviously for your component or for your module. So a lot of things happen there before you decide, but then there is a track for doing a more full-scale release test.
How long does it take to test the system?
That's less than a week. So actually, the cut-off time for getting something in to the next weekend's release, I think, is Thursdays. So then there is some decision, and then there is baselining of that environment, and then there is test going on, and then there is essentially a change board on the next Thursday, which decides what goes in. So it's less than a week, and that's also something that we continuously try to compress with automation and so forth.
We also do tests in production to check the sanity.
Yes, we verify. I mean, we do say canary releases or being able to enable features for a specific user or release something for just one broker out of our whatever number of brokers, and so we're, yeah, that happens a lot throughout. Good. Thank you. Now it's lunch, I guess.